All right. Hello, everybody. All right, so here's exam 2 we're going to go over today, kind of give you feedback on that. Turns out I was pretty lenient and maybe just the fewer opportunities to lose points. Gave a pretty generous average here. So you'll see. And then for, I think 2 or 3 of you, I even gave 1 bonus point for the very last question because I was really happy with the particular answer that 2 or 3 of you gave. I'll explain all that shortly and probably give you a quick overview in a minute after I pass these out. So I'm going to pass them out, so I'll take a couple minutes. And again, please pardon my any mispronunciations. I'll do my best. All right, Cameron Davis. I'm just going to go ahead and move this table a little bit so I can navigate as I need. Matthew Hogue. Hunter Klebert. Anna Corey. Michael Rader. Rachel Passantino. Ian Marmon. Andre Bernard. Sydney Kramer. Kyle Bro. Ariel Williams. Jacob Hartley. Jesse Allahan. Caroline Weber. Lucas Savani. Andrew Broussard. Emily Steinheim. Asher Mudge. Jacob Gonsolin. Mason Mitchell. Samuel Daigle. A lot of high numbers here. Didn't bother, I guess. Well, I got it mostly right. Caleb Julian. Sarah Graham. Bo Gotro. Caleb Fosino. Nicholas Rivera. Emilio Lambert. Daniel Hecker. Bragg Mountry. Samuel Sweat. Jason Spears. Gwyneth Alexander. Daniel Bryant. Abigail Melling. Anthony Champagne. Jack Amanda. Sorry. Ricky Nguyen. Zach Gilbert. Philip Nguyen. Jessica Guam. Edward Farron. Nathan Mahoney. Trace Norman. Madison Tandrella. Javier Santiago. Daniel Nunez. Paula Menendez. Evan Batten. Connor Smart. Brooks LeBlanc. Clayton Bravo. Matt James. George Gonzalez. Sergio Garcia Orozco. Joanne Coleman. All right, who did not get theirs? Okay, who else? Everybody else good? All right, so as you see, most everybody did pretty well, and quite a few of you did very well. I promised to make it up for you on the final exam, make it really brutally difficult. I'm kidding. This is like a fair bit easier or more lenient than I would typically kind of intend to do. Not that I'm like intending to be really harsh or whatever. Just the typical what I find is the average is closer to 80 than 90, right? So I think exam 1 was probably 77 or 78. and that's somewhere typical. So probably a little more difficult than this one, at least in terms of the grade outcome. You'll notice like maybe I could have taken off more sometimes or whatever. But ultimately, you probably have a good impression now of what the final exam will be like, kind of in reference to this. I am aiming to grade you based on how much I can tell you learned, and if I screwed up making the exam, then that's kind of on me. So I'm not going to penalize you for that. Okay. So I think let's just get into it. Any questions or concerns? Big picture. Oh, one thing I was going to say. The final exam, we have a little extra time, and so the way I design it is it'll be 50% of it will be the old stuff, so from exam 1 and 2, and then the other 50% is kind of the content we've done since exam 2. So it's one of the reasons I want to go over this with you, make sure to clear anything up. So you can kind of expect maybe a question on each of the first exam, second exam, and then 2 or 3 questions on the remaining content. Something like that. It kind of depends on how long or involved I make the questions. Maybe a couple smaller ones from one of the others. And the other thing to note is, as you see, the content really is building on itself throughout the semester. So in that sense, all of it's cumulative regardless. But about 50% will be specific to the stuff we've been learning since exam 2. Okay. So let's get to it. Problem 1, we had 3 Olympic swimming pools to keep clean with granular filtration. And so that was a bit of an interesting problem in that we had these 3 pools, and instead of having a typical flow, we were just going to flow through, kind of in a recirculating manner, so that our residence time was essentially we could get a flow rate from the residence time, but we said that the residence time it just needs to turn over once a day or once every 3 days or whatever. So our granular filters we can envision as cylindrical units, and the water would be flowing like that. And so the area involved is the area of the circle, pi r squared. We could probably find the volume of these, but I don't think we need to. The volume for the swimming pools, so that we can find from the fact that we have 3 swimming pools, and they are each 2.5 million liters, right? So we'll say 3 times 2.5 million liters. So that would be the same thing as 75, if we convert it, 7,500 cubic meters. So I'm just going to divide by 1,000 for cubic meters, and I'm going to multiply that by 3. That 25 times 3 is 75. So putting all those pieces together, we get a total volume like that. So each one would then be 2,500 cubic meters for the volumes of the swimming pool. If we solve the area for these the filters, each filter has an area of 1.227 square meters. And if we solve for the flow rate, given that we know the residence time to be 24 hours, that should be V over Q. So then we can solve for the flow rate that's going to be going through our filters, and we can get that accordingly to be 312.5 cubic meters per hour. Okay, so some mistakes on this problem were just in the setup. You need 3 filters, not 1, and just kind of have to read and catch that. Another aspect was determining the timing of when are we backwashing and figuring out the times for each piece. So I didn't take off much if I saw this was kind of your only mistake, but the wording here says the filters are pressurized and are operated at a high rate, blah, blah, blah. So we've got a rate for filtration, a rate for backwashing, and then it says the filters automatically backwash and rinse after 24 hours of filtration time. So it even says filtration time there. So the filtration time is 24 hours. Now, a fair number of you made the mistake of saying that's the cycle time. Understandable mistake, and it's not throwing your numbers off too far. But if you see the final answer here and you're like, well, I was close, this is probably why you weren't actually on it, because you treated this 24 hours as the total cycle time, not the filtration time. So then the problem also describes that there's 15 minutes for the rinsing and the backwashing each. So 15 minutes is a quarter of an hour, so I'm just going to say 0.25 hours. And that would mean we don't have any time for like air purge. There was no mention of that. So that would mean the total cycle time is 24.5 hours. Okay, from there, it's pretty straightforward. We just have to calculate the numbers and ultimately put in our equation for effective filtration loading rate. That equation is VF minus VB minus VR all over the area times the total cycle time. Okay, so then we solve for each piece. This should be for the volume filtered, 441.8 cubic meters. Volume rinsed should be 4.6 cubic meters, and the volume backwashed should be 7.7 cubic meters. Here's another possible mistake. We have a separate backwashing versus operating loading rate. So we have, when we calculate those volumes, we need to use the specific loading rates. So we could say the lowercase v for the loading rate. I think we usually call it VA, right? That's the 15 meters per hour, whereas the lowercase v with a B for the backwashing rate was 25. Okay, so that's the explanation for the difference in volume there. That's another mistake a few people made. So with that, we can calculate the effective loading rate to be 14.3 meters per hour. And I think it was only 0.1 or 0.2 off if you had calculated it with the wrong filtration time. And I probably took 1 or 2 points off, right? If that was the only thing that happened, it wasn't a lot off. Okay. Any questions on that? We good? Okay. Okay, so next up we ask how many filtration units are required to keep the pools clean. I ask you to answer in a whole number. And here's a point where if you didn't get the previous part right, of course, it's going to be difficult to get this one spot on. So I had that in mind. I was trying to check to see, well, did you have the process approximately correct, even if your previous number was wrong. So if you got the wrong answer, I probably still took some off, but as long as you had a reasonable looking process, that was most of the credit. Okay, so the flow rate we had to meet was this 312.5 cubic meters per hour. And one way to approach this is to say, well, we need to meet that with the effective loading rate, which has accounted for all the downtime and everything, times the area for each filter, right? So the effective loading rate, that's meters per hour. If we multiply that by an area, then that gives us some total flow rate. But we have to meet that with some number of filters. So what we can do is say the area per filter. If you want, I'm gonna write it out a little more explicitly than I normally do. So area divided by one filter times the effective loading rate, which is going to be meters per hour. So this would be meters squared. This is going to be meters per hour. And multiply that by number of filters. So if we're tracking the units, the filters will cancel, right? That's kind of how we get to a raw number. Okay, but it's going to be the area times the REF times that number that we're solving for. So we can solve for the number of filters, and when we put in the numbers there, which we had already got, This comes out to a value of 17.8, but that means that we cannot meet the demands on 17 filters, and we're not going to install 0.8 of a filter, so we have to round this upwards to 18 filters. Okay. All right, so next up, and as always, stop me if you've got questions. Next up, we have what is the filter efficiency, and answer this in percent. A nice thing about this part was you didn't really need to get part B correct. And in fact, you could probably even have messed up partly on part A. So long as you had the timing right, this would come out, the timing and the fact that there's different loading rates for backwashing versus filtration. And then you could get this one just fine because our formula is just simply the volumes. It's volume filtered minus volume backwashed minus volume rinsed over volume filtered. So even if you messed up some part of the equation to even find the volume filtered and stuff, but you had the right ratios in place, the timing and the backwashing rates, it actually turned out fine. You could answer this problem, or you could get the right answer correct, rather. So this comes out to be 0.972, or I asked it in percentage, so that should be 97.2%. Okay, make sense? All right, so then next up we say during the off season, the pools are used less frequently. The operators have a lower hydraulic residence time, therefore, so they're not used as much, they don't get as dirty. We don't have to flush them through the filters quite as fast, basically. So we can use a slower flow rate. And the question is, how many filters would be needed if the recirculation flow was reduced to provide a residence time of 3 days? So basically, we're dividing it by 3, right? We were flushing every day, and now we're flushing it so that the entire volume passes through every 3 days. So residence time is now 3 days. That's still V over Q. And so we can, we'll call this 72 hours is 3 days, right? So from there, we can get a Q should be a third of what we solved for previously, so 104.2 cubic meters per hour. And then do the same thing we had. Now, if we were, if we thought about it, we might be able to say, well, we can just divide our prior answer of number of filters by 3, and it should work out, which is pretty much the case. So we can do our same little process here. Effective loading rate times the number of filters times the area of a filter to solve for the number. That comes out to be 5.94, which rounds to 6. Excuse me. 6 filters needed. That was weird. All right, so that's the approach there. And one thing you'll notice is if you had these steps right, and I actually stopped on this problem, if I saw that your number here, whatever this number was, if you're taking this approach, even if you had the previous problems wrong, if that number was a third of the number you solved for in B, and then you rounded up appropriately, I think I gave you full credit. I might have put an X and said okay, or something like that. I think maybe if I took off credit, it would be 1 point, but I don't think I even took that off. Okay, so that's that problem. All right, so next up is the botched problem. So I'll show you here where I was trying to simplify it for you, and I messed it up. I took out this highlighted text here that said, so this is a membrane problem. I'll read the whole thing, and then I'll describe the issue. So the problem that you saw said that you were tasked to design a membrane system for a small community. The required flow rate is 0.1 cubic meters per second. The temperature of the water ranges from 5 degrees Celsius in the winter to 25 in the summer. The chosen membrane has a maximum transmembrane pressure rating of 200 kilopascals and a membrane resistance of 4.2 times 10 to the 12th per meter. So part A was fine. It asked what is the required membrane surface area for this application, and you could give me an answer for that. So I'll discuss that in just a moment, but to explain a little bit about what went wrong, normally when I had previously formulated this question, I also included this, which I was just trying to simplify things a little for you. It says, based on previous experience, you know that the operating TMP pressure should be no more than 80% of the max that it's specified for. So having that in the question would make parts B and C actually make some sense. So if we were limiting it to like try operating lower than the maximum, that would be why. So that's maybe helps explain why B and C made no sense once I removed that. All right, so I'm going to answer A here, and then I'll kind of comment on B and C so you can just have a feel for what I was intending to ask. Okay, so for this part, we need to know the required surface area for the membrane. I guess we'll say area of the membrane. And we can relate that to a flux value. And we can relate the flux value to this resistance. So essentially, we're going to use two equations, one that relates area to flux, and one that relates flux to pressure and membrane resistance. So a couple things we know. We've got a flow rate here provided 0.1 cubic meters per second. And we have a membrane resistance, RT, total resistance provided 4.2 times 10 to the 12th per meter. And we can look up our dynamic viscosity values for both the summer and the winter. That would be 8.9 times 10 to the minus 4th in the summer. And in the winter, this would be 1.518 times 10 to the minus 3rd kilograms meters per second. Okay, so those are the pieces of information that we need. And we can continue and say, well, our flux, to solve the area, we have an equation that says that's going to be equal to the QP divided by the area of the membrane. That's going to give us what we can solve for area. So area then is going to be the flow rate that we need to provide across the membrane divided by the flux across the membrane. And that one's pretty simple, straightforward, intuitive. That's kind of the definition of a flux. It's a flow across an area. Now the other equation that we need will be how the flux relates to the transmembrane pressure, which is taking that pressure divided by mu times RT. So when we put in those numbers, that's 200 kilopascals. We're going to have to convert that to pascals. We'll use the two different mu's here for each calculation. And of course, the RT is 4.2 times 10 to the 12th. So recognize that pascals are a unit that is expressed with newtons, essentially. So that's kilograms, seconds, and meters. And our mu is in kilograms, seconds, and meters. And our resistance value is in meters. So kilopascals would be in kilograms, megagrams, kilometers, and kiloseconds, right? So we need to convert the kilopascals to pascals. So once we do all that, we should be able to solve. We'll get flux values for each of them and then plug that into our equation. I'm just going to skip a little bit there and say that the area during the summer required, and in class I went ahead and told you to provide answers for both. The question technically is, the best way to answer it would be to to derive or to find both answers and then decide which one is the minimum necessary, right? So the larger one is the minimum necessary, because if you need more during the summer or during the winter or whatever, then that's the one you need to design for. So I went ahead, even that I kind of clarified in a way that made it a little easier, because then I was just looking to see if you had the right answer even if you didn't select it. Okay, so area in the summer should have been 1869 square meters, and in the winter, 3188. So that means this one is the required surface area for the application. Okay, does that make sense? Good on that? Okay, part B said how much fouling resistance can be added to the membrane before the maximum pressure is reached. And if I were to include that and do it properly, we could have just said, let's say, if you're operating in the summer, how much space do you have? Or we could say, using that 80% limitation that I removed from the problem, then we could look at that difference in pressure that's required and calculate how much resistance that would correspond to. So we could have done that. Like I said, I told you not to answer it because it didn't end up making any sense. Part C then said what percentage of the total resistance is contributed by the fouling resistance you solved for in part B. So that would just be what portion of the total resistance, given that kind of that change, what portion of that is the fouling. So that's just dividing the fouling resistance by the total resistance. Okay, so that's, don't worry too much about all that. That was my bad and bank error in your favor in terms of grades. Okay. Any questions on that? Concerns? All right, so problem 3 was an equilibrium chemistry question, kind of disinfection, tied a couple things together like that. And by this point, I recognized the error. You know, if you were doing the exam in order, then this was coming after the confusion and maybe you only had 20 minutes left. So again, I was aimed to be pretty lenient here, even though it was 40% of the grade. So the problem says bromine and chlorine are very similar, and active forms of both can be used for disinfection of recreational water. Let's consider a case of a 10 cubic meter pool. Typically, the pool has no meaningful flow of water in or out and is well mixed. So that's basically going to tell us it's a batch reactor, right? No meaningful flow and it's well mixed. Batch reactor. Okay. For this example, we will assume disinfection caused by the OCl minus or the OBr minus is always negligible. So we don't really care about that. The following table provides some constants for the disinfection of resistant pathogens. I made another tiny mistake that I don't think it bothered many of you. That resistant pathogens, I meant to write that here too. So I don't think it bothered you. Yeah. Okay. So we've got this table, got some information, and essentially the equilibrium chemistry that we've done several times by now with the chlorine is going to be essentially the same thing we need to do with the bromine. It just has a different constant for where that equilibrium, that dictates the equilibrium. Okay, so part A says, how long would it take to remove 99.8% of the resistant pathogens from the pool if enough chlorine was applied to achieve 1.5 milligrams per liter of HOCl? Now, some of you embarked on this problem and thought to yourselves, oh man, I've got to do all this chemistry. Let's go. I'm going to do this equilibrium chemistry and figure it out. But the way I wrote this made it easy for you, if you recognize. It says we added enough chlorine to achieve 1.5 milligrams per liter of HOCl, which is the disinfecting one. So right away, for the part A, you don't actually need any chemistry aside from the knowledge that the way I wrote that is saying that we have that much HOCl to work with. So if you did work to figure out from 1.5 at a given pH that wasn't actually given, and you tried to figure out how much of it you would have, kudos to you for trying, but you didn't need to and you didn't have enough information at that point. Okay, so what we need to do here then is to take this batch reactor and do a mass balance on how fast these bugs are going to die, because we do have a rate constant. Now this is K, and if we recall from the disinfection stuff, we need to recognize that we could also describe a K star that is K times C. That's why the units look a little funny, even though it's first order, a disinfection process. So we need to recognize a couple things. That's one of them. And the other is the 99.8% of bacteria. That's going to correspond to how much is removed, which is 1 minus how much is remaining. So this would be the fraction removed. So to write that mathematically, so the fraction remaining is n over n naught, right? So 1 minus n over n naught equals 0.998. So that means n over n naught would be 0.002. And we've seen that a lot. This time I put it at a 2 instead of a 1 there. Doesn't really matter, but should feel rather familiar. So we're going to develop our mass balance essentially saying we have some change in pathogen concentration over time in that volume, and that's going to be equal to, in that volume, the rate that stuff is happening, right? That's going to be K times C, and it's well mixed, so we're going to say that's to the 1 power. Yeah, VKC. Right, so the V's cancel. And let me rewrite this, I'm sorry, that should be dn dt. And we need the n over here also, right? So first order, so it's n to the 1 power. Okay, so with that, then we solve our mass balance. And we've done this a lot, so maybe you didn't even worry about this part. We integrate, and we get natural log. Oops. We get the natural log of n over n naught equals e to the minus k c t, and we go from there, right? So, and we're going to assume this lowercase n equals 1. All right, so with that, then we basically say we can solve this by saying that's 0.002, and then all we have to do is realize we need to put the k and the c in, and we can find our time, right? We can also write this, by the way, that's, sorry, I did that a little bit backwards. So n over n naught is equal to e to the minus kt, the natural log of n over n naught. Just jumping ahead of myself here. That gets rid of the exponent, right? That's why we do that. And then we can say, set that equal to the natural log of 0.002 and solve for time, right? Because we have all these pieces. So in this case, our K for HOCl is 0.123. That's liters per milligram minute. And our concentration was 1.5 milligrams per liter, which is pretty convenient there. Okay, so all of that gives us a way to solve for time, and then time, therefore, should be 33.7 minutes. Okay, so I think that if you tried to do anything with the chemistry, that probably would have ended up a little confusing. If you tried to do anything with a CSTR, that would also be confusing. There's no flow rates. So the mass balance definitely will not work out appropriately that way. And you kind of had to recognize that this 99.8%, how to translate that to n over n naught is 0.002. Okay. Any other questions or issues you had with that? I think most of the mistakes fell into something like that. All right, so the next problem, part B, is essentially the same. We just have to do it with HOBR. So really all we do is change K. We have K now at the new value 0.0098 from the table. Liters per milligram per minute. Put it in the same way otherwise, and you get a time of 422.8 minutes. Okay, so basically the same problem, and I probably did not take off much points if you got the other one wrong, and just a point or two maybe, and also got this one wrong. Okay, part C and D then were also fairly similar process-wise. You just had to do this on the two different ones. And this was a problem we've done a fair bit, but it still threw some of you for a loop. What we're looking for is the fraction of chlorine that would be in the form of HOCl if the swimming pool had a pH of 7.8. So what we're looking for is the fraction in the HOCl state per total. And the way to get here is to use two equations. The reason we need two equations is because we technically have two unknowns, right? We have the unknown of how much HOCl is there, and the second unknown, if you want to call it that, is the how much OCl minus is there. So what we need, in a way, is a system of two equations, one of which is our equilibrium constant, which we know the equilibrium itself looks like this. So that means our equilibrium constant is going to be the products over the reactants, H plus, multiplied by, some of you made a mistake to add them here, times OCl minus, divided by HOCl. So if you tried to add those, that was a mistake. And if you flip to your formula sheet, I think it even, I didn't include it. I think we have it on the formula sheet, that equation. So you have to check. And it is multiplied there. Okay, so that's the first one. And the next one is we simply need to know that the total molar concentration of chlorine is going to be equal to the sum of the OCl minus and the HOCl. And from here, we just do algebra to solve and find our result. So I find the easiest way to do this is to simply write up the fraction that we're looking for based on this total. So we can say the percent HOCl will be equal to essentially the HOCl divided by total and then work with this equation until I can plug in something from the equilibrium equation to get it and to simplify and to have one fewer unknown. Of course, we have to multiply this by 100% if we're getting percentage, but we asked for fraction, so we're not going to do that. We'll say fraction. Okay, so with this equation, we can start simplifying, make it just a little cleaner by dividing the top and the bottom by HOCl. So that'll give us 1 over 1 plus OCl minus divided by HOCl. And from there, we can substitute something to get rid of some of the unknowns, get it to the point where we can solve it in terms of Ka and H+. So given any combination of a equilibrium constant and in the H+ in this scenario, we can figure out that fraction. So when we rewrite the Ka equation, we can rewrite it just simply dividing both sides by H+. So Ka divided by H+ would be equal to the OCl minus divided by HOCl. Okay, so that means we can substitute this in right here. So we can get our answer by saying, let me do this a little. That means we can find our answer by saying it's 1 divided by 1 plus Ka over H+. So H+ is, if the pH is 7.8, H+ is 10 to the minus 7.8. That's from the pH. And then we can know our answer. So once we do all of this, the fraction becomes 0.355. I think if you had done most of this or something very close, but you had added, I saw a lot of people getting something like 0.55 as a value. So that was a fairly common one, and I could see you were mostly on the right track. So like I said, I tried to give a fair bit of credit for that. Part D was essentially the same task. So again, I wasn't wanting to be too redundant with taking points off, but in total, if you botched this process, you would have some total number of points off for this page, basically, which still is well over 50% of the credit that you got. Okay, so in this case, we do the same thing, and we can describe it in the same manner, 1 over 1 plus. In this case, it was OBR minus divided by HOBR, but it comes out to be the same exact derivation. So we'll say Ka for the OBR system divided by H+. So the only difference is we use the other K, and we get a fraction of 0.864. Okay, any questions, issues on that? All right, so the last problem here, I was hoping that it would kind of stretch you a little to tie in the previous problems, the parts A through D. And I was hoping also that when you gave the reason why, you would call back to kind of the numeric values or perhaps provide some quantification here. Of course, a lot of you didn't, and I wasn't too upset by that. But what I especially liked is if you did. So like I said, I did actually give a couple of bonus points here if you really, really nailed it. So you'll find that kind of no matter what answer you gave, whether it was right or wrong, I was actually looking at the justification, and I wanted to see the fact that you were thinking about both the portion of the disinfectant that was in like the disinfection type, the HOBR or the HOCl, and the speed at which it was happening. So that's like parts A and B and parts C and D. I wanted to see both considered in whatever answer you were giving. Even if you got A, B, C, D wrong, if you were considering it in those terms, you would have had full credit. And then if you did some math on top of that to say, okay, well, it's this amount, you got +1 credit. Usually, if you had no consideration of, let's say, the rate, but you did consider the portion, I would give you all but 1 point. So it was worth 8 points total. Or vice versa. If you considered the rate but not the portions, I probably took off a point. If you considered neither, and it wasn't much of an explanation, you probably had more points taken off. But even still, it wasn't too many. Okay, so the way I would really like to see this approach is to realize that you can find a rate for a given system that's negative k Cn, right? Or we could write that as k star, or not equals, but we could recognize k star is k times c, right? So a couple ways you could account for both the portion and the rate would be to calculate a k star for each system. Or you could go a little step further and just, you could assume some arbitrary concentration, or you could just take the fraction that was, right? So if you say for the HOCl case, k star is equal to the k that was given times some arbitrary concentration times the fraction that you solved for, that would work. Fraction that it was HOCl. And you could do the same thing with HOBr, with a k star kc times the fraction that was HOBr. And you could give some answer like that. Now, what I did was I just made an arbitrary assumption that, oh, let's call C1. And then that makes this very simple. You're just taking the k times that fraction. You could have used the 1.5 that was used previously. It doesn't really matter too much what you do with it, but you can make that comparison as so long as you compare them equally like that. So I'll just write out what I showed. I even had somebody just write in text, well, this one was 10 times faster than the other, and so even though it was like 35% compared to 80%, the difference there should make the faster one the better one regardless. Now, I also saw a couple of answers that I liked that said, well, maybe HOBr is more toxic, and so maybe we don't want that. That was an interesting way to think about it. And I think one of you also said something about, well, time's not really too important. It's just sitting there. It's got a lot of time. So we're going to go with the one where you need less of the material. So if you give me something a little more thoughtful and creative like that makes some rational sense, good for you. This is the way I was thinking about it, was to calculate, let's say, a k star for HOCl. I went ahead and put that as arbitrarily 1 milligram per liter for the C, multiplied that by the 0.355, the fraction, and multiplied it by the K for HOCl. That gave me an answer of 0.044 per minute for HOCl, and the K star for HOBr did the same thing, 1 milligram per liter times that 0.864 times the rate constant for HOBr, and that came out to be 0.0085 per minute. So then I decided that HOCl was kind of the better one because it was faster acting, and you're going to ultimately need to use less chlorine there. I say faster acting, but per amount of chlorine we add, or per amount of disinfectant, it is the faster one based on that rate constant, that K star. So this was the kind of tying it together. As you see, you didn't really need to do any calculations to answer it. I was very happy if you did, and kudos to you if you did. But all in all, I tried to give a lot of credit regardless if you gave me some thoughtful response. All right, any questions? Concerns? What did you think about this problem? Did you like having to answer like that, or did it throw you off? It's fine because I graded it all right? Okay. All right, so I think that's it for today. So we'll see you on Tuesday. Yeah. we'll resume the BOD discussion then, kind of plot out the rest of where oxygen demand goes in a lake or river or stream. Okay, have a good weekend.